Let's pick up with the significant figures. Significant figures, as I said, is very important because in dealing with the data and the factors that you're going to use to do your analysis and your solutions, you have to make sure that what you are using for your input data matches your output data, i.e. your result. So in looking at significant figures, you have to determine how many digits you have, how many figures you have both before and after the decimal point to make sure that you have the same level of accuracy in your result. So let's look at an example. We're going to measure the area of a rectangular plate. We assume an accuracy of 1/10 of a centimeter, 0.1. So if we look at the rectangular plate, we have on the long side 16.3 centimeters. On the short side, we have 4.5 centimeters. So on the long side, our length, using our accuracy that was given to us, plus or minus 1/10 of a centimeter, the length is 16.3 plus or minus 1/10 of a centimeter. So we have a range here. The range is 16.2 centimeters to 16.4 centimeters in terms of the measured three significant figures for accuracy. So we've got 2 centimeters on one side, or 1 centimeter on one side, centimeter on the other side to deal with. So we've got a little bit of wiggle room here. Doing the same thing for the width, the short side, 4.5 centimeters plus or minus 1/10 of a centimeter gives us 4.4 to 4.6 centimeters, measured to 2 significant figures. So we've got 2 ranges here of accuracy and significant figures. On the long side, we've got 3 significant figures. On the short side, we have 2 significant figures. Note that the significant figures include the first estimated digit. Okay? So for us to do anything with this mathematically, we have to keep those in mind. So if we're wanting to calculate the area of this rectangular plate, we're looking at the surface area. We have 16.3 centimeters times 4.5 centimeters, which gives us 73.35 centimeters squared. So now we are calculated to 4 significant figures. You can't get more accuracy by using a solution that doesn't match the input. The input was 2 and 3 significant figures. So this answer is not a justifiable answer. So we deal with the rule of thumb. The rule of thumb says when multiplying several quantities, the number of significant figures in the answer is the same as the number of significant figures in the least accurate of the quantities being multiplied, where the least accurate means having the lowest number of significant figures. The same rule applies for division. So we have 3 significant figures, 2 significant figures. When we took the product, we had 4 significant figures. All we can have, the least accurate, is 2, the 4.5, 2 significant figures. So we would have to round this up or round this down to come up with an accurate answer. The dimension 4.5 centimeters has only 2 significant figures. So rounding down, we end up with 73 centimeters squared. Realizing the value can range between 16.2 centimeters times 4.4 centimeters, which gives us 71 centimeters squared, or 75 centimeters squared. Okay, so 73 becomes our rounded figure, and it is within the range of 71 to 75 centimeters squared. In dealing with significant figures, zeros may or may not be significant figures. Those used to position the decimal point are not significant. So in these two examples, 0.03 and 0.005, in each case, the zeros are only positioning the decimal point. So with the first one, the 3 is the only significant figure. In the second example, the 75 are the significant figures. So the leading zeros in this decimal do not make the cut in terms of significant figures. Suppose the mass of an object is given as 1,500 grams. This value is ambiguous, so it's better to use scientific notation to get a more accurate answer. So if we move the decimal place 3 to the left, 1.5 times 10 to the third grams, we end up with just two significant figures. If we add a 0 after the 5, keeping the same 10 to the third, we now have 3 significant figures. If we put 2 zeros back in there times 10 to the third, we have 4 significant figures. Likewise, if we have an expression that has 4 zeros ahead of the 2 significant figures, 0.00015, expressed as scientific notation, we reduce the value down using the factor of 10 to the minus 4, by moving the decimal point 1, 2, 3, 4 places to the right, and depict the exponential then as 10 to the minus 4, because we moved it 4 to the right. We have now 2 significant figures, 1.5 times 10 to the minus 4th. Because those zeros are not counted as significant figures, they are only used and present to locate the decimal point. So in general, a significant figure is a reliably known digit other than a 0 used to locate the decimal point. Now, the rules for addition and subtraction are a little different. When numbers are added or subtracted, the number of decimal places in the result should equal the smallest number of decimal places of any term in the sum or the difference. So as an example, I have 123, 3 significant digits. I'm going to add 5.35 to the answer to that value, and I will get 128, not 128.35. Okay? The 123 has the smallest number of decimal places, understood to have a 0.0 here. 5.35, though, has 2 decimal places. So this has a larger decimal place value than the first. So we cannot carry the 0.35 forward as part of the answer and for it to remain accurate or justified. In another example, 1.0001 plus 0.0003 gives us 1.0004. 1.0004 is correct to 5 significant figures because both of the terms, 1.0001 and 0.0003, both have 3 decimal places. Okay? So that value then stands as a good number. Likewise for subtraction, 1.002 minus 0.998 gives us a difference of 0.004. 0.004 has 1 significant figure and is correct. Okay, this is because we had the correct number of significant figures, 1.002 and 0.998 in our two terms. They both have 3 decimal places. Looking at another example here, we have a room that is 12.71 on the long side, 3.46 on the short side. Recall the rule of thumb for multiplication. We're going to find the area here by doing the product. 12.71 meters times 3.46 meters gives me 43.9766 meters squared. That value cannot be used, okay, because it exceeds the significant figures. You can only claim the number of significant figures in the least accurate of the quantities being measured, or in this case, terms in your product. So we have 4 significant figures, 3 significant figures. We have to use 3 significant figures. So the answer, the difference, has to be reduced down to 3 significant figures, and we do some rounding. So in this case, since 3.46 meters has 3 significant figures, the result can only be expressed as 3 significant figures. So our answer then becomes rounded up to 44.0 meters squared. When we come back, we'll look at orders of magnitude. And looking at this, we get a sense of looking at values and solutions and getting a gut feel based on the powers of 10.